Welcome to your next installment of Physics Strangeness. This 10 to 15 minute clip will be on virtual particles, and I will be your quantum coordinator, Robert Nemiroff, teaching at Michigan Tech. So if you're just tuning in, this is called Physics X, Extraordinary Concepts in Physics, and it's being taught for credit. I'm trying to review the concepts as best as possible because most classes deal in the math and trying to go light on the math. You can see this on iTunes, or you can see this on something called Starship Asterisks, then search for Physics X. I'm sure you can find it. Just try. All right, virtual particles. These things are strange even for quantum mechanics. So in the previous lectures, we've seen some very strange quantum phenomena, but this is possibly the most strange. Virtual particles are somewhat controversial. They pervade all of space and time. They're everywhere all the time. They're less well, in my opinion, understood in the uncertainty principle. I don't completely understand them. I don't think anybody does. They're related to the uncertainty principle. Once again, I will be trying to raise you to my level of misunderstanding, telling you some cute facts. These things are used in calculations. As I said, things about them are controversial. They are, however, somewhat real in the sense that they're needed to explain static forces such as electricity. Who's seen electricity? Magnetism, this strong nuclear force, a good force that holds our nucleuses together. Weak nuclear force and gravity. I, for one, am fond of gravity. Maybe gravity. Gravity is controversial. Technically, general relativity doesn't use virtual particles. It just has curved space. But people hope there will be one day a quantum theory that will incorporate gravity, which may or may not rhyme with string theory. And if so, then quite likely, possibly, it would have things called gravitons, which would be virtual. And real, but virtual as well. Well, there are real gravitons. Anyway, virtual particles, as I said, are needed to explain attractive force. So one of the things that bothered me a lot when I was studying physics is how you get attractive force at all. If you throw tennis balls at somebody and they throw tennis balls at you, it seems that you're only generating repulsive force. Yet gravity is attractive. Positive and negative charges, they attract. What is this thing attractive force? I don't get it. And I didn't find a satisfactory answer that I was happy with in my books. So I've investigated this a bit. I'll comment on it here, but it's strange stuff. Anyway, virtual particles do make real-world differences. They are seen, we'll review a little bit here, the Lamb shift, Casimir effect. Quantum electrodynamics makes good use of, for example, virtual photons, and is a very good theory in that it makes very accurate predictions. So ultimately, physics exists to make predictions. So physicists are like psychics, except we don't try to predict who's going to marry who. Physicists try to predict exactly how much acceleration something will see, or the velocity after a certain amount of time. So quantum electrodynamics is really good at these predictions and can use the virtual particles in their calculations to be good in 1 part to 10 to the 12th, which is really good. Quantum chromodynamics also uses all kinds of virtual particles in their calculations. A virtual particle, technically, is a particle that, well, one of the attributes is it does not obey this famous relation, special relativity relation involving energy and momentum and mass. Therefore, virtual particles are declared to be off the mass shell. They have a non-classical relationship between kinetic energy and mass. They can have negative momentum. So we'll stop and pause on that. A virtual particle can have negative momentum. It can be moving left to right, and if it hits you, you move the opposite way. They can have any speed, and we'll review some of that. I'm proud to repeat stuff sometimes because I believe people don't get things on the first try. I certainly don't. So virtual particles, as I said, don't obey this. They tend to destructively interfere over long distances. They have a range limited by the uncertainty principle, particularly if they have mass. So high mass virtual particles can only go a certain amount of time, a certain amount of distance away. So for instance, the virtual particles involved in the strong nuclear force wouldn't go far outside the nucleus. Whereas things like electricity would have virtual photons that could go arbitrarily far away so far as we know, given that the photon, we don't know the mass. The photon mass is so low we don't know it. Virtual particles are defined really only in perturbation theory. They're a way of doing calculations, but even so, they're quite real in the sense that they predict things like the Lamb shift we'll review. The further off the mass shell virtual particle is, the less the probability amplitude in many quantum mechanical calculations. One somewhat controversial area is, tell me more about these virtual particles. Do they, for instance, conserve energy? And the answer is yes, no, and maybe so. So the real particles that are affected by virtual particles may conserve energy. Now, general relativity doesn't conserve energy over long scales, but generally on local scales, most things do. So the real particles do. Once created, it is usually assumed that a virtual particle will have a definite energy that does not change. When being created, some people consider that the energy is just borrowed from a neighboring real particle, which would fluctuate inside the uncertainty principle. However, that's a little bit controversial because some people consider that virtual particles can be created in pairs. Particularly, they would be in pairs if they were trying to be, you would have to have if you had a charge-uncharged pair, so you could have an E minus and an E plus, and then you wouldn't have to just have one charged particle, virtual particle zipping around. If they came in pairs, if there's some quantity that needs to be conserved, like electric charge, then there would be they would be born here, they would annihilate there without a bang, they would just disappear, and there would be always conserved charge. Ultimately, though, the existence of virtual particles is interpreted from the mathematical frameworks of quantum theory. And some of these have infinities, which can cause debates as to what virtual particles are and what measurable quantities they might create. So virtual particles are completely hidden by the uncertainty principle. They are living on the other side of delta x, delta p less than h. The s is h bar over 2. That's a detail. So technically, you can't grab one. It's hidden by the uncertainty principle. However, something very interesting happens related to the Unruh effect. When a real particle accelerates, some of its virtual cloud of particles, so you consider that, let's say an electronic charge here is sitting there. You can consider that there's all these virtual photons popping in and out all over it, a cloud of particles. If you accelerate this electron, if you accelerate any charge, you get a real photon. That's just like if you accelerate any mass, you get a real graviton. So anytime you move, you're creating stuff. You're creating gravitons. If you're charged, and it's hard to be completely uncharged, anytime you move, you're also creating photons. One way to think about this is that you're shaking free virtual photons. You're making virtual photons into real photons. The acceleration causes some to cross the uncertainty principle barrier into the real world. And once they're in the real world, they can be measured by real world detectors. Find this strange? So does everybody. Okay, but there's real stuff going on here. A slight shift in the energy levels of orbiting electrons in a hydrogen atom is called the Lamb shift, and it has been measured. It's caused by an interaction between the orbiting electron and surrounding virtual electrons and photons. It's a unique test of virtual particles in quantum electrodynamics. That's what this stands for, QED. Quantum there's the E, dynamics. That's the theory of the quantized electric magnetic fields that's good to 1 part in 10 to the 12. So looking at that theory in detail, they said, hey, wait a minute. These hydrogen atoms, they should be showing something, Lamb said. Then he went out and measured it, big time, got it right. So that's an effect of virtual particles. Casimir effect. So Casimir, some people go out and they try to go to high energy accelerators and look through powerful telescopes. Casimir studied his lunch. He was eating mayonnaise, and he was wondering why it flowed so slowly. So it turns out that the particles in mayonnaise have some kind of strange attraction to each other that isn't predicted classically. Extrapolated, that strange attraction allows parallel plates to attract when no classical force indicates they should. So if you take 2 parallel plates and you put them really close to each other, Classical physics would say, oh, cool, you have two parallel plates really close to each other. But quantum effects would say, oh, no, they're going to attract. They're going to attract pretty strongly, too. Actually, I think it's a distance to the fourth effect. And the reason is virtual particles. Actually, the lack of some virtual particles, because some virtual particle modes can't survive in the cavity in the middle. And so the lack of those, on the outside you have all the virtual particle modes over here pushing and pulling, but in the middle you're missing some because they're standing waves, things drop out, interference, and you get an attraction, a strong attraction. So the 0 point energy of the vacuum has changed. These plates, the classical example of two plates close together leads to an attraction, but there are ways of constructing things so that you get a repulsion as well. So the Casimir effect does not only have to be attractive. If forces result from exchanging virtual particles and the corresponding real particles always have positive mass, how can the force be attractive? This is the thing that I've wondered about for a long time. So the answer is that virtual particles can carry negative momentum, as I indicated earlier. Interference with other virtual particles can determine attractive or negative, whether you see it in attractive or negative momentum. And the calculation can get complex, but really what happens is if you have something here, you have a person here, and you have a person here and they're charged in opposite ways, then you can emit there can be a virtual particle that moves here and there, but that creates a force that goes in the other direction. Remember, these things are off the mass shell. Math is complicated. To get into the details, which I don't completely understand, you'd have to get into the guts of quantum electrodynamics. Can they go faster than light? Yes. Strangely enough, virtual particles can do lots of things. Virtual particles are a little bit like Superman or Superwoman. They can go faster than light, they can go slower than light. Those can be the terms that take them off the mass shell. However, you can't communicate faster than light. That seems to be a universal effect. No communication, FTL, faster than light is what this means. FTL, faster than light. So two well-separated observers, so we can go back to our Alice and Bob over here. This could be Alice, A, Bob, B. They could be measuring fluctuations in a field. And they would say, oh, field got a little stronger, oh, field got a little weaker. And they would each be doing that. That could be attributed to virtual particles zipping around faster than the speed of light. However, just like in versions of entangled particles, the correlations between the observers' fluctuations could only be found later. You can't predict what fluctuations you will see. Unpredictable. Because it's unpredictable, it puts a limit and you can't communicate faster than the speed of light. Strange stuff. Black hole gravity. Here's another thing I used to wonder. How is it that gravity gets out of a black hole? There's a good link under here, so you might want to click there and see discussions on the FAQ of physics, and also there's also other discussions. So first of all, general relativity doesn't really have virtual particles, so it doesn't have this problem. General relativity just has curved space. It's the curved space that causes things. So gravitons, virtual gravitons, don't have to get out of a black hole. They don't need to go there. So, but people think that general relativity isn't really the final word on gravity. They expect there is virtual gravitons around, and how do they get out of a black hole? For instance, how does a charged black hole? How does a magnetic field get out of a black hole? Well, some gravity. Another thing I didn't say is that it's possible when things fall into a black hole, and we're going to do a lot of black hole stuff later in this, because things build up around the event horizon. They fall in actually, but as far as we see them, they appear to build up there. So some of it hasn't fallen in. So that's another reason why gravity can get out of a black hole, because it's built up around the horizon. However, it is quite possible and does have an effect that virtual gravitons can come from the inside and go out. Now, the black hole can only stop. The reason why it's a black hole is because light can't escape. But if something can move faster than the speed of light, it should be able to get out. Similarly, the virtual photons of the electric and magnetic fields should be able to get out of a black hole. Now, we haven't been able to go right up to a black hole and see this, but that's what we expect. However, these things cannot carry messages again faster than light. So here's a quote that I haven't been able to find attributed to any one person. It's really food for thought. All photons are virtual photons. It's a statement that gets debated in some physics boards a lot. Since photons travel at sea, they experience no passing of time between emission and absorption. That's one reason why one might consider that all photons are virtual photons. They're also treated as mathematically similar in many quantum calculations. Also, you might consider that when a photon's moving along, it's continually changing into all kinds of things. Other photons, virtual electron, positron pairs, all kinds of stuff as it goes. And only when the photon is absorbed does it really have to give up its true photonicity. So not only does an electron have a virtual photon cloud, but a real photon can be considered to be participating in this sea of strange particles that are virtual particles that are being created all the time. It's continually jumping around into many different things. And these are shown by integrals. You have to integrate over all the things it can become many times when you're doing quantum mechanical calculations. So real particles, though, can trigger real detectors, but virtual particles can only transmit force. So I'll close with a thought that I've wondered is, do virtual particles respond to gravity at all? So this, again, we don't really have data on this. I actually wrote a paper questioning whether even in our solar system this could be seen. Do virtual particles, or are they also immune? They can get out of a black hole, but what about the solar ones? Even if they're going faster than the speed of light and get out of a black hole, do some of them, are they deflected by gravity in any way? Or are virtual particles automatically, no matter what's around, no matter what the universe has, no matter what black holes have, they just fly straight as seen from infinity. They're always in flat space. So there are many things about physics that we don't understand, and this, I think, is something that I'd like to see better investigated in the future. And with that, I will close and ask you to keep Schrodinger away from your cat. Thanks.